Last time, sorry. So last time, what were we doing? Yes, we were wading through 1.6, which is we were using quantifiers in arguments. And mainly this, the idea was use universal instantiation, or use instantiation, or generalization to move from quantified statements to unquantified statements. Quantified statements to, yeah, unquantified propositions. And we saw at least one or two examples of this last time, right? Of an argument where we worked with quantifiers. I think I did a kind of a longer form argument at the end of last class, right? Is that true? I think it's true. Anyways, what I want to do today is I want to discuss briefly two other valid arguments that involve quantifiers, but then we're going to move on into chapter 1.7 with proofs. And this will allow us a much more open playing field with which to kind of explore these ideas. So we're only going to spend a little bit of time in 1.6, and we're going to move right on to 1.7 today. Okay. So let's discuss these last two valid arguments involving quantifiers. So two more valid arguments involving quantifiers. We have this one, which is called universal modus ponens. Which says the following. If you have a for all statement, for all x in a domain, p of x implies q of x, and then you also have PA for a particular element A in the domain, for A in the domain, then what do you all think we can conclude from this?
Q of C?
Yeah,
Or is it
Q of A.
Oh, A.
Perfect. I can actually barely even read your comments. This might be a rough Zoom lesson because something is messing up with my Zoom. So if I can't read what you write, just speak up, I suppose. But yeah, we can conclude Q of A. If we have for all x in the domain, P of x implies Q of x, and you have P of A for some particular A, then you can conclude Q of A. Very good. And then the other one is going to be universal modus tollens, which is just the following. If we have a proposition for all x, P of x implies Q of x in a domain, and then we have not Q of A for a particular A, what can we conclude?
Not P of A?
Yeah, not P of A. Unfortunately, all that I see from y'all's writing is just A, which I believe that you probably didn't mean to say. So something is really messing up with my Zoom. Sorry. But the answer would be, yeah, not P of A. Great. And let's do a brief example on this before we go into chapter 1.7. So as an example, here's a nice example. All lobstermen set at least a dozen traps. Hamilton is a lobsterman. And we're supposed to conclude from this argument that Hamilton sets at least a dozen traps. So let's try to make this into a formal argument where X is the domain of all people. So the domain of X is all people. So what should we use to translate the first sentence?
For all X, S of X.
For all X, for all people, what we need is something involving lobstermen, right? So if we denote by L of X is a lobsterman, then what should L of X, what should follow this?
Implies S of X.
Yeah,
Sets
perfect.
At least a dozen traps.
This should be S of X. So for all X, L of X implies S of X is sets a dozen traps. At least a dozen. Right, okay, and then what is the statement, Hamilton is a lobsterman?
That would be just L of Hamilton.
Yep, L of Hamilton. This is the proposition, Hamilton is a lobsterman. And then what argument do we use?
Universal modus ponens.
Exactly, by universal modus ponens, we conclude that S of Hamilton, or Shamilton. So in other words, Hamilton sets at least a dozen traps, and hooray. So at this point, I think that we have all of our arguments, all of our valid arguments that we need in order to start doing actual mathematical proofs. So does anyone have any further questions before we proceed to the next chapter, where we start actually employing these to prove some things in a more mathematical setting? Questions? Okay, so everyone's happy with how we have incorporated quantified statements into our valid arguments. I will assume that the resounding silence means yes.
A quick question.
Oh, hang on. Can you still hear me?
Yes.
Yes.
I think my microphone might be dying. Let me change something around. This class is getting rough. Let's see. Okay, now things should be better. What's your question?
So Do you remember when we learned about like negation and double negation and like identity and implication substitution? Do you remember that?
Yes, I do.
I hope so, because you're the teacher. So when are we supposed to use those as opposed to using the arguments?
So let's see. Those logical equivalences are things that you can use at any given point in an argument. So for instance, I think we'll see some examples of this further on, but here is maybe a bit of discussion. So for instance, in some cases, we're going to be asked to prove a statement that looks as follows. So for instance, actually I can do a literal example that we'll see later on today. So prove if mn, so m and n are integers, prove if mn is even, then n is even or m is even. Okay, so let's kind of discuss what we're trying to prove. If e of x means that x is even, what I'm trying to prove here is that e of m times n implies e of m or e of n. Do you agree with this?
Yes.
Okay. It turns out that the way that we're going to prove this is by proving something different. What we're going to prove is we're going to prove the contrapositive, because we know that P implies Q has the same truth values as not Q implies not P, right? So if I want to show that E of m times n implies E of m or E of n, I can alternatively prove that the contrapositive is true, namely the negation of E of n or E of m implies the negation of E of m times n. So this is a case where in the sequence of a logical argument, I used a logical equivalence in order to change what I'm trying to prove.
Okay, that makes sense.
Right, and then of course, what we're going to do is we're going to use De Morgan's, because what is the negation of the proposition E of n or E of m?
Isn't it P implies Q? No, that's implication.
Right, here we're trying to negate a proposition where I have one proposition or another proposition.
Wouldn't it be not E of n and not E of m?
Exactly,
Okay.
not E of n and not E of m. What is the, well, we don't technically know this yet, but essentially this collection of logical substitutions leads to the following proposition. What this actually means is if n is odd and m is odd, then m times n is odd. And it turns out that this is an easy statement to prove. And this is more easy to prove than just using the definitions of something being even implying an or statement. So here's an example where we use logical equivalences to change one proposition, which is maybe not so straightforward to prove, into a different proposition, which is going to be more straightforward to prove. Does this help answer your question?
I think so. So would we use arguments to do a similar thing then, or?
Right. So.
I'm sorry. I know this is a little bit off topic, but I've been really confused.
It's a very good question. I would say that the idea is as follows. The overarching structure of what we want are arguments. Arguments are the thing that, like, eventually we want to prove things, and what proofs are valid arguments. And when you're doing an argument, you want to be able to do logical substitutions on any of the propositions that you see. A very basic example is the following. Let's talk about first modus ponens. Modus ponens says if you have P implies Q and you have P, you can conclude Q. Well, we've also discussed modus tollens, which we've called a different proof technique, but it's actually just modus ponens with an additional logical substitution. So modus tollens says if we have P implies Q and we have not Q, we want to conclude something. But what we have here is if we have the proposition P implies Q and we have the proposition not Q, is there a logical substitution we can make for P implies Q?
Contrapositive.
Yeah, the contrapositive of 1 says, well, we can exchange P implies Q for the statement not Q implies not P. And now if I have the proposition not Q implies not P and the proposition not Q, what can I conclude using modus ponens?
Not P.
Not P, right? This argument says this implies this, and if you have the hypothesis, you get the conclusion. Well, I've exactly used that in this case. I have a hypothesis, namely not Q, and I know not Q implies not P, therefore I get not P. So what this example shows is that really you should think of the argument of modus tollens as a combination of the argument of modus ponens with a logical substitution. Does that help a little bit?
Yes, thank you.
Yeah, so essentially we're going to be building more and more complicated arguments, and many of those steps will involve doing a logical substitution somewhere using one of the propositions that we have. Okay, that was a great question. I'm always happy to answer questions, but that's a very good one. Any other questions?
I have a question.
Yeah, sure.
I really don't know when to read what chapter. I usually just fill out the class and then I just read the next chapter, or not chapter, but section. Is there a guide that we can follow anywhere?
So you're right. Someone asked me that at the beginning of this class, and I said that I hope that things will be clear what to read next. I admit that things, I suppose, haven't been so clear. Maybe I should start doing that at the beginning of each day, saying what I plan on covering today and the next day and so on. The next days, I'll be covering 1.7 and 1.8. So if you want to read ahead for the next couple days, I would say it's in these sections that you should read ahead. Do you want more information than that, or is that?
No, that's good.
Okay.
As long as you do every class, I think I'll get it. Yeah, I'm good.
Okay, yeah. Thank you for kind of holding me to that. Yeah, I should make sure that I make that clear.
Thank you.
Mm-hmm. Any other questions? Also, another thing is that going forward, we won't skip around so much in terms of sections. So going forward, we'll start a chapter, and then I'll tell you which sections in that chapter we're going to read over the next, how many weeks. So it should get better than chapter 1. Any more questions? Okay, let's then move on into section 1.7, which is going to have the introduction to proofs. So this is proofs. First, we have a bunch of definitions. So first of all, what is a theorem? Definition. A theorem is a statement that can be shown to be true. Usually mathy. We also use the word proposition. Usually at the top of the totem pole is theorem. So these would imply kind of big results. Lower down on the totem pole would be proposition. And there's something that's even lower that I'll get to in a little bit. I'll just say it, lemma. So these are in increasing order of difficulty or challenge. Okay, so what is a proof? A proof is a valid argument that establishes the truth of a theorem. Okay, an axiom or a postulate is these are statements that are assumed to be true. Can someone name me any famous axiom or postulate?
Aren't like the like vertical angles are identical? Isn't that a postulate?
Yeah, exactly. When you were doing geometry, you probably got a basic toolkit of postulates. For instance, axiom, all right angles are similar or something like that, right? Probably the most famous one is the parallel postulate. Does anyone know what the parallel postulate says?
Does it say that parallel lines never touch? I'm just taking a guess.
It's close to that, yeah. Yeah. So what the parallel postulate says is the following. Let L1 be a line in space, a line in the plane, and let P1 be a point not on the line. Then there exists a unique, so exists a unique L2 line passing through P1 such that L1 intersect L2 is empty. Or in other words, L1 and L2 never intersect. At least I believe this is one formulation of the parallel postulate. To be honest, it's a little hazy in my mind, but essentially the idea is, given a line and a point not on that line, there exists a unique line which is parallel through that point, which says that the two lines never intersect. So if you take this postulate as one of your defining postulates, then you can produce a geometry from this. Like there are a whole bunch of things that you can prove that you might, do they still teach geometry using like angles and parallel postulates and stuff like that? I'm actually not sure. I see.
Someone in the chat said sadly.
Sadly, okay. Well, geometry is beautiful, so I hope that you've seen at least a little bit of this. Okay. And the last thing is some further definitions are lemmas. These are easy theorems. And corollaries.
Can you clarify how to spell that? Is it L-E-M-M-A?
Yeah, L-E-M-M-A, a lemma. It's a nice word. And then corollaries are theorems that follow easily from other theorems. Maybe I should call them results that follow easily from other theorems. Okay, so we have produced a bunch of new language that we will use to discuss these proofs. Any questions on all these things that we've just talked about? Everyone okay? Everyone having fun? It's Friday, early in the morning. We're doing math. Okay, with that resounding affirmation, let's continue. What we're going to do next is we're going to introduce some of our first math definitions. And essentially, we're going to be using these math definitions as our sort of playground where we're going to prove a bunch of things using these definitions. So definitions, and these will be most of our definitions for chapter 1.7. All of these are going to be important, so you should work a lot with these. Okay, some first definitions, our first mathy definitions. An integer, n in z, so n in z just means an integer, so this is a little redundant. An integer n in z is called even if there exists k in z, another integer, such that n is equal to 2 times k. An integer is odd if there exists an integer such that n is equal to 2k plus 1. And this is also called the parity. So two integers have the same parity if they are both even or both odd. Okay, that's one definition. Any questions on things being even or odd? No? Okay, let's do another definition. Hopefully these aren't too unfamiliar. An integer, a in z, is a perfect square if there exists an integer b in z such that a is equal to b squared. That's what it means to be a square. You're the square of something else. And last definition, a real number, r in R, so I use this boldface R for the reals. A real number is rational if there exist P and Q in the integers, Q not equal to 0 such that R is equal to P over Q. If an integer, or sorry, if a real number is not rational, it is irrational. Okay, so a bunch of problems that are going to be coming your way today and Wednesday. Oh yeah, there's Labor Day. Today and Wednesday are going to be involving these definitions, okay? So you'll get plenty of practice with these. Let's actually get started on proving some things. So our first proof strategy. Sorry, there's a lot of baggage that has come along with this lesson today. First proof strategy is direct proof. To prove a statement, say P implies Q, or really, secretly this is for all X, P of X implies Q of X, it is sufficient to show that for all, or for an arbitrary A in the domain, P of A implies Q of A, right? This is one of our logical rules. If we have P of A implies Q of A for A arbitrary, what can we conclude using universal generalization?
There exists Q of A.
If we have this for A arbitrary, really this is kind of meaning like for every A, so to speak. So here it's going to be a for all X in the domain, P of X implies Q of X. So what I'm saying is that this direct proof strategy that we're going to be practicing in just a moment comes from the following argument form. If you can show that P of A implies Q of A for an arbitrary A, then you can show that for all X in the domain, P of X implies Q of X is a true statement. This is a valid argument. So if I want to show that this is true, it's enough to show that this is true.
How do you show you picked an arbitrary A?
So we will get exactly into this in just a moment. That's a great question. The idea is that you want to show that whatever process you do can be done for any element in the set.
Okay, cool. Thank you.
I think that the following example will make this more clear. So as our first example, let's prove if n is an odd integer, then n squared is odd. Okay. So what we're going to do is we're going to do something for an arbitrary odd integer. So let me do this first proof, and then we can see what I do. So let n be an odd integer. What is the definition of an odd integer? Can someone remind me, even though it's no longer up?
The 2n plus 1.
that there exists a k such that n is equal to 2k plus 1, right?
Yeah.
Then, by definition of odd, there exists an integer k such that n is equal to 2k plus 1. So here, I've got a particular odd integer in mind, but the properties that I'm asserting about it hold for any odd integer. Okay, so I've used the definition of odd to say if I've got an odd number in hand, then I can find another number k, another integer k, such that n is equal to 2k plus 1. Now I want to show that n squared is odd, so then n squared is equal to what?
2k plus 1 squared.
Yeah, 2k plus 1 squared. And what's this equal to?
4k squared plus 4k plus 1.
4k squared plus 4k plus 1, which I can rewrite, can be rewritten as 2 times 2k squared plus 2k plus 1. Since 2k squared plus 2k is an integer, we conclude that n squared is odd, because it can be written as 2 times an integer plus 1. Are there any questions about what I've written here?
How was that a direct proof?
Okay, yeah, so I should discuss this as follows. So what the real statement here is for all x, where x is an odd integer, x is odd integer, I'm trying to prove, actually, here I just want an integer. X is an integer. For all x, such that O of x, which means x is odd, then this should imply that O of x squared, right? What I'm trying to prove is that for all integers, if the integer is odd, then the square of the integer is odd. Do you agree?
Yes.
So if I wanted to write down what I did here in this kind of formal notation, the first step that I did was I used universal instantiation, where I said, assume, let's see, so O of A, essentially. So if I have this statement, for all x, O of x implies O of x squared, what I want to do is first, or the idea is I want to show that O of A implies O of A squared for an arbitrary A. And so remember that a valid argument is one where you can conclude the conclusion from the truth of the premises. So what I want to show in order to show that O of x implies O of x squared is I want to show that whenever the premise is true, namely my integer is odd, then the conclusion is forced to be true, namely the square of A is odd.
That makes more sense.
Right. So to show an implication, right. I think if I keep repeating it, it'll just sound more and more like a jumble. But the direct proof for a statement like this is you show whenever you have the first property, it forces the second property. So I took an arbitrary odd integer. I showed that for an arbitrary odd integer, its square was also odd. Therefore, I can conclude for all odd integers, their squares are also odd. Any further questions here? Shall I do another?
Yes, please.
Certainly. Okay, but first let me give a little more time. Does anyone have a question about this proof? Okay, let's do another example. Prove that the product of two rational numbers is rational. Okay. So once again, I'll kind of say the idea that I want to do is what this statement really is trying to show is that this is really kind of a for all statement. For all x and y pairs of rational numbers, then the product x times y is a rational number. And the idea of the proof is to use universal instantiation, where I say, let me take two arbitrary rational numbers, and then I only use properties that are true of all rational numbers. So that's kind of what it means to show that something holds for an arbitrary rational number, for an arbitrary element of the set. Let me do this example, and then we can discuss kind of this this arbitrary element sort of thing. Okay, prove that the product of two rational numbers is rational. So what I do is my first step is universal instantiation. So let R1 and R2 be rational numbers. Note that I'm not picking specific rational numbers. I'm not picking 1/2 and 36/7. I'm saying let R1 and R2 be rational numbers. And then what can I conclude by the definition of rational numbers? By definition, what?
R1 is equal to P1 over Q1.
By definition, there exist P1, Q1, P2, and Q2 in Z. There exist 4 integers such that Q1 and Q2 are not equal to 0, and R1 is equal to P1 over Q1, and R2 is equal to P2 over Q2. Here's what it means to be working arbitrarily. I'm never actually fixing R1 or R2. I'm not actually picking numbers here. And similarly, I'm not picking actual integers that when you divide them, they give you R1 or R2. I'm just saying, if I take an arbitrary real number, then by definition, there must exist integers such that this relationship holds and such that this relationship holds. Is this okay so far? Okay, we have our two rational numbers. We want to understand their product. Then R1 times R2 is going to be equal to what?
P1 over Q1 times Q2 over P2.
Times P2 over Q2, right?
Oh, yeah.
And what
yeah.
is the product of rational numbers? How do we multiply these?
straight across. So it'd be P1 times P2 over Q1 times Q2.
Exactly. Okay. Now, P1, P2 is in Z. It's an integer, right? If you multiply two integers, you get an integer back. Q1, Q2 is also an integer because I took two integers and I multiplied them. Last question, Q1 times Q2, can this be 0?
No,
Right, Q1, Q2 cannot be 0. Why is that?
because it would make it undefined.
Well, that's not quite the way that we should argue. It's true that we don't want it to be 0 because we haven't defined what dividing by 0 means, but the argument is that Q1 and Q2, neither of these were 0. And in the integers, if you multiply two things that aren't 0, can you get 0 back?
No,
No, exactly. Q1, Q2 is in Z, and Q1, Q2 is not equal to 0 since Q1 and Q2 were not 0, since neither Q1 nor Q2 are 0. So since I can write R1 times R2 as an integer divided by another integer where this integer that you're dividing by is not 0, what do we conclude?
That R1 times R2 is rational.
Yes. Thus, by definition, R1, R2 is rational.
So I have a question on that.
Yeah, sure.
So what if P1 and P2 and Q1 and Q2 are the same numbers? Because I'm thinking that like if it ended up like 30 over 30, which is just 1, would that be considered rational still?
Yep, definitely. It's because it satisfies the definition. Nowhere in the definition does it mention that the numbers have to be different in some way, right?
Okay.
And in any case, we certainly want 1 to be a rational number because, as you said, it can be expressed as quotients of integers. Namely, take any non-zero integer and quotient it by itself, and you've got 1. So 1 should absolutely be a rational number.
Okay, cool.
Any other question here? So there are two remarks that I want to discuss kind of again using these two examples. Let me see if I can try to kind of describe what the process is. In both of these statements, we're secretly being asked to prove a quantified statement. For all odd integers, n squared, for all odd integers n, then n squared is odd. Or for all pairs of rational numbers, their product is rational. And so what I do is I immediately kind of disguise the switch from a quantified statement to a statement for arbitrary such things. So here, I immediately switch from if n is an odd integer, then n squared is odd. This is kind of a for all statement. For all O of n implies O of n squared. What I immediately switch is to, I want to show O of A implies O of A squared for arbitrary A. And then how do I show such an implication? Essentially, what I want to show is that the truth of this follows from the truth of this. So as long as this thing is true, this thing must be true. As long as I can show that, then this proposition is never false, right? Like, let me kind of go back into the logic of it. So here's how I think about this. I start off wanting to prove for all n, O of n implies O of n squared. The first thing that I do is I use universal instantiation or universal generalization. Really, I use universal generalization to say if I had O of A implies O of A squared for arbitrary A, then I could conclude for all n, O of n implies O of n squared. So now what I want to show is O of A implies O of A squared for arbitrary A. So want to show that O of A implies O of A squared for arbitrary A. I want to show this proposition is true, always true. Now the question is, if I have an implication, when can an implication be false? What's the only way to make an implication false?
Where it's true implies false.
Yes, the only way for an implication to be false is if P is true and Q is false. Then P implies Q is false. And so my job is to show that this never happens. So I show that this never happens. So I want to show this is true. The only time this would be false is if I had an odd number whose square was not odd. So I show that that never occurs by showing that whenever I have an odd number, then its square is odd. So then I can conclude O of A implies O of A squared for an arbitrary A, which finally lets me conclude for all n, O of n implies O of n squared. I hope that this was not confusing, but rather helpful to see why I write these proofs in the way that I do, and why I then start by let R1 and R2 be rational numbers, because I'm showing for an arbitrary pair of rational numbers that, you know, if R of R1 and R of R2 implies R of R1 times R2. I want this to be true. So what I show is that it's never the case that I have a rational R1 and a rational R2 and an irrational R1 times R2. And that's exactly what I showed here. I've already held you over. Actually, I've held you over kind of late. Do you have any questions about especially these two proofs? I think that the proofs are more digestible than what I was discussing here. I wanted to write this page so that you can see how we're using the framework of logic that we've built up in order to do these proofs. But I think these proofs are more straightforward than the background that I was just discussing. Any questions? Okay, well, have a wonderful Friday and a nice weekend and a wonderful Labor Day.
Thank you.
Thank you.
Thank you.
Thank you, you too.